that you raised that string field theory is non-local, but I mean, you don't see it in Olaf's formalism.
Yeah.
And I think one way to understand is that he has made a field definition to remove all the second derivative and third derivative terms, right? I mean, because your action is only single derivative, powers of single derivative, right?
Yes.
And this is after field definition, right?
Right.
And that's the reason why you are not encountering the kind of problems that you will see if you take a generic non-local action which has an infinite number of derivatives acting on the field. And I think it is in the same spirit that you can write string field theory action which has an infinite number of derivatives, but it's also possible to make a field redefinition to write it in the form of these Lovelock terms, where you have many parts of single derivative terms, right? And their initial value problem is perfectly well defined because you have a canonical formulation.
But I think the problem is that again, the perturbations in general will not preserve it. So then you are back to the old problem.
No. I mean, the point is, you can take in his case, it was independent of certain dimensions, but I'm saying that let's imagine that you write the effective action in Lovelock kind of terms, okay, where you only have, in all terms in the action, only has powers of single time derivatives. Then the initial value problem is completely well defined there, right?
Sure.
And so, I mean, you can say that will be the so from the point of view of string theory, right? String field theory, of course, is more general. It can give it in a formalism where you have multiple derivatives, right? But to set up the initial value problem, right, you should probably first go to the formalism after a field definition so that you only have multiple powers of single derivative, single time derivative, and then you can set up the initial value problem. So I think
perhaps also if you go away from the limit, I mean, you can always go back to the infrared limit, and in the infrared limit, you set up your initial conditions and say, if I pump in more and more energy, how my system will behave in the UV.
No, I'm thinking in the position space, just normal time derivative, right? Normal time evolution, right? I mean, the problem with setting up time evolution in a non-local theory is precisely that it looks like you need infinite amount of data initially, right? Because you have infinite derivative action. But if you make a field definition to make it into multiple parts of single derivatives, then that problem doesn't exist, right? Because then the differential equations are all second order, and you need only the field and its time first derivative to be specified as an initial data.
That's true. That I agree. But my point was that to Olaf was that, I mean, okay, so we have to keep in mind that this is true, as you said, with the field redefinition, plus we have to preserve the symmetry of OD, D.
No, you don't need OD, D. For this, what I stated is completely general, right? OD, D is for a special case, when that metric is independent of certain directions. And so, of course, there, for generic cosmological perturbation, this symmetry, it's not invariant under OD, D. But the fact that you can make the action into multiple parts of single time derivative instead of having multiple time derivative, that is independent of OD, D, right?
Does that mean field redefinition removes somehow non-locality? Is it always possible?
Okay, I think it has not been established that it's always possible. But I think whatever you know, I mean, it seems that the string effective action after a field redefinition can always be written in terms of powers of single derivatives.
So, let me put it this way.
Has someone tried to do that for string field theory, or
pardon?
Is it possible to formulate string field theory in a way that this sort of comes out automatically?
Well, yeah, that will be, of course, very nice, but I don't think that has been done. Right?
Okay.
I mean, string theory has many formulations, and one formulation is easy for one thing, right?
Yeah.
There is probably no single formulation which is easy for everything, right?
Right.
And
but that in principle could be a goal, right? That
that could be a goal. Yeah, to rewrite string field theory in a way which has only single derivatives.
Yeah.
Right, multiple parts of single derivatives. That will certainly be very nice, right? But
and when you say this, you mean strictly string field theory redefinition in terms of string field. Somehow, you mean rewrite string field theory?
Yeah, you make a redefinition from the string field, right?
I see. Okay, since I'm chairing this, I see that Terry Tumbulis is raising hand.
Yeah.
So
So when you say you rewrite things in terms of single derivatives, but is now the dependence on the single derivatives local or non-local?
Well, I mean,
local.
you've
I mean,
Yeah, sorry.
what is
arbitrary
it?
part of single derivative.
Sorry?
It's arbitrary. It can include arbitrary part of single derivative, but it's completely local. It's like DBI action, right? It has like square root of determinant of G mu nu plus F mu nu, right? It has only single derivative of A mu, but infinite parts of the field strength.
nice.
But
Right? So it's in that sense.
what we say it's local in single derivative. So it's a like a cutoff at let's say what order in the dependence in single derivatives.
See, DBI action, for example, it's square root of say eta mu nu plus F mu nu, sorry, square root determinant of eta mu nu plus F mu nu. And because of the square root, it contains arbitrary parts of F mu nu. But nevertheless, the field equations are always second derivative in time.
But that's a real problem, that how can you do it to the closed string sector? It's not so easy problem also.
Yeah, but closed string sector, we know that we can do it to any derivative order, right? We can do it. For example, if we look at the Riemann square term, right? Riemann square term has a second derivative, right? It has to, so the action contains second derivative of H mu nu. But once you write by field represented in the Gauss-Bonnet form, then it only has multiple parts of single derivative. Right? It has four parts of single derivative, right? Similarly, the next Lovelock term will have 6 parts of single time derivative. So this expansion doesn't stop. I mean, it goes on forever, right? Otherwise, of course, you will not get you will be finite theory. But it's still that now, as I said, I mean, I don't think it has been established that you can do it for arbitrary action of this kind. But it seems quite plausible. And the reason is that if you look at the poles in the S matrix, right? At a given mass level, there are only finite number of poles. Whereas if it was genuinely non-local, if you really needed an infinite number of boundary condition, right? I mean, you can think of it that if you do this geometric quantization, then the number of initial conditions that you need determines the number of degrees of freedom, right?
Mm-hmm.
And string theory, you know, has only finite number of degrees of freedom below a given mass level. Right, so that also suggests that this is the correct way to rewrite string theory, so that you don't have this initial value problem. That the initial value problem is well defined in the theory.
I don't agree with that, because in a general non-local field theory, right, you can have a standard analyticity structures because you have ordinary propagators, let's say, and so you have not an infinite number of fields. You have a finite number of fields, but they are interacting non-locally, that's all. Provided, of course, the non-local vertices have, you know, quite stringent conditions so that you have the standard analyticity structure of the amplitudes. And I mean, that also relates to something you said in your talk. I mean, you approach this from the point of view of the analyticity structure, from the point of view of those mathematical papers by these French people long ago. But, you know, we don't have to, I mean, this stuff was investigated in the 60s very thoroughly, directly in momentum space, of course. You know, there's this famous book of the analytic S matrix summarizing the stuff. So you don't need, you know, to go through the X space derivations at all. You simply look at momentum space directly. You start from the Euclidean regime, which defines the original analyticity region D that you mentioned. And then you can essentially, as long as you can deform contours and close contours only in the finite complex plane, you can derive the standard analyticity structure of amplitudes. So you can apply all this. This is a paper by Paul Chin and myself 2 or 3 years ago. you can derive the standard analyticity structure of amplitudes in all those models that include also this, the models that mimic the string field theory Feynman rules, directly in momentum space. And but you cannot derive, general dispersion relations because those, of course, need that you close the contours out at infinity, which is impossible with the non-local kernels. But otherwise, the standard emergence of normal thresholds, anomalous thresholds, the other types of singularities, ACK nodes, etc., that occur in field theory, you can have them, they emerge naturally also in the non-local field theories, including string field theory, as long as the vertices are essentially entire functions and have appropriate, some other appropriate properties. So yeah, I mean, that's another point I wanted to make concerning analyticity structure. And also, of course, the fact, as you said, that in general non-local theories, you have this potential infinities along the Minkowski axis now, because k-square becomes indefinite in sign. That's, of course, an extra constraint that you don't have in string field theory, but of course, you can apply the extra constraint in non-local field theories to make the kernels also convergent in along the Minkowski real line, in addition, of course, to having this in Euclidean. Because Euclidean, of course, the basic formulation, right? You define everything in Euclidean space and then you analytically continue. That's the only possible way of defining these theories.
Yeah,
so it's a pure.
I mean, you need probably convergence in all directions in the complex plane.
No, that's impossible because you have, of course, entire functions. That's entirely impossible.
To have a discussion, yeah, but to have a dispersion relation, you have to close the contour, right? At infinity.
No. You cannot close the contour at infinity. Right? I mean, that's precisely the point. That so you cannot derive standard dispersion relations. That connects also with what.
I think string theory has standard dispersion relations, right? Because the S matrix is convergent at a complex infinity.
No, we're talking about the Feynman rules of string field theory, right?
So off-shell Green's function has this problem of divergence, but I'm saying the on-shell S matrix.
No. Once you go on-shell, the amplitudes, of course, are then physical amplitudes, right? But I'm talking about the Green's functions, how you define the Green's functions. Right.
Yeah. But in a generic non-local field theory, if you try to use these non-local vortices, I think it will be very difficult to have the amplitudes converge in all directions in the complex S plane, right? Complex Mendelssohn plane of Mendelssohn variables.
Yes, yeah.
And why do you say it is very difficult? It should be rather impossible.
But well, depends. There are various sectors, right? I mean, it's.
Somehow it's a magic of on-shell condition, right? I mean, it certainly, we don't expect this to happen off-shell, but somehow string theory achieves this on-shell.
On-shell, yes. On-shell,
but it doesn't matter in the end, right? If in the end, when you go to physical momenta, you have a well-defined amplitude that has, the expected properties, then you're fine, right? I mean, after all, you compute cross sections in the end, right?
Yeah, but by physical amplitudes, you mean complex momentum, complex on-shell momentum?
On-shell, on-shell S matrix elements, right?
For real S.
Yeah.
But I mean, if you want dispersion relation, you do want complex momentum, but still on-shell, right?
Right, but those you cannot have, right? You can have them, of course, on the finite plane, right, where you include a finite number of singularities.
Yeah.
But in the end, all you need, right, is to be able to compute cross sections in a well-defined manner that that gives sensible answers, finite answers.
Yeah.
Yeah, maybe we can move to some other raised hands. Richard wants to comment, I believe. Richard, can you unmute yourself?
Okay, I had one comment about the localization and then just a question. The comment was one other way of seeing that it's basically hopeless to do it is finiteness, right? If you want the loop amplitudes to converge, it's those factors of e to the minus p squared that's making them converge. I don't think there's any way to get rid of them, at least not with any finite number of positive string fields, positive norm string fields. The question is to Ashok, and that is, if I've understood correctly what you're saying, and I don't worry about amplitudes possibly growing at large at large Minkowski energies, then I can do the same non-localization to an ordinary field theory. I don't need the infinite number of degrees of freedom. I don't need even the supersymmetry. Is that correct?
That's right. Yeah, yeah. I think if you didn't worry about the bad growth in the Lorentzian direction in the Minkowski amplitudes, then you can. It looks like you can certainly do it.
Yeah. So one more question by Anna. Anna, can you unmute yourself, please?
Yes. My question is again about analyticity properties of scattering amplitudes, of physical amplitudes. And my question is whether we can find out that in non-local scalar field theory, at least, these amplitudes has essential singularity at infinite value. For example, if you take forward limit amplitude, can we conclude that they must have essential singularity at infinite S?
Yeah, I think I would not say that they must have, because we know that string theory amplitudes don't have. But generically, I think they will have, because generically they will grow as exponential of S, and there'll be essential singularity at infinity. Right? But we know certainly examples in string theory where it doesn't happen.
Okay. I just would like to point out that there was a recent paper by Junsei Takuda in which he repeated kind of repeated the proof of Martin-Broussard bound for non-local theories, and his result is that under some weak assumptions, he obtained that the at least forward scattering amplitudes or amplitudes at finite t are polynomially bounded. Of course,
What is this paper again? Can you?
I can put it in Zoom chat in a few in a few minutes. I can put this reference. But his result is that under some analyticity assumptions and assumption that amplitudes are bounded exponentially, he obtained that actually they have to be bounded polynomially. Repeating the proof, the same proof for Martin-Broussard bound, where you start from polynomial boundedness and come to the boundedness by power 2, as by power 1, by power n. So Martin-Broussard bound says that amplitude has to be bounded by s logarithm squared of s, kind of that.
But for what interactions? I mean, this. What is the statement? What kind of interactions?
It's just a general assumption that the amplitude in non-local theory is bounded by exponent of s to some power. From this, it follows after
what
some
amplitude? I mean, Euclidean amplitude. In what direction? I mean,
it's physical Minkowski amplitude in at finite exchange momenta t.
But that depends on the interaction.
Yes, but if you assume something, you can derive some formal conclusions about
No,
this.
no, no, no.
I think in that case,
That's impossible.
I think it doesn't consider really like non-local field theories in this sense. He puts non-locality in the spectral function. So he consider like non-localizability of Jaff, I think, yeah. And he assumed this non-localizability. So like spectral function can grow like exponential of some power of S, where S is the Mandelstam variable. So it's the spectral function which is non-local. Okay, so but the starting Lagrangian is still like the starting kinetic term is still local. It's purely.
Well, they do not specify the starting Lagrangian.
Huh?
They do not.
They don't specify it. Yeah, they don't specify an interaction. They just put non-localizability in assumption in the spectral function, and they try to generalize the usual bounds on the amplitudes. Okay, with us, because usually what we assume on the spectral function is that there is some kind of polynomial boundedness. Okay, so in this case, what he does, he considers these classes of strict normalizability, quasi-localizability, and he study how the bound of the amplitude changes if you change the starting assumption on your spectral density. So the paper is the one that is now in the chat. So I don't know if.
No, but those results are old. I mean, Arthur Jaffe did that in the 60s, right? Exactly what Luca is talking about. I mean, these general assumptions about localizability and polynomial versus non-polynomial bounds in the spectral functions, right? And then what this implies for the amplitudes. I mean, there is a literature on the subject. I don't know if there's some recent twist on that, but yeah, I mean, yeah, that's all.
What the paper is that he gets like positivity bounds for this kind of non-localizability.
Yeah. Okay.
Yeah, but if we start from non-local Lagrangian, wouldn't we obtain the same?
No, because that depends on the. I mean, you can have interactions, right, that are both convergent along the Euclidean axis and the Minkowski axis, or only along the Euclidean axis. I mean, in fact, that's an extra constraint from the point of view of local field theory, which you don't have to put in string field theory, as I was saying, because you have these cancellations there between different parts of the interaction. Even though, again, this hasn't really been shown in explicit detail, but you expect so if you reproduce the standard string amplitudes.
Oh, but my point is that if you start from non-local Lagrangian itself, then if you start from the concrete non-local Lagrangian, I expect that you can compute the amplitude and find these Weidmann functions and so on, and just apply the arguments which were derived for them.
There are no Weidmann functions.
Well,
Weidmann functions are the ones that you get from Euclidean space continuing directly in X space to Minkowski space, right? In non-local field theory, also in string field theory, that's not what you're doing. You start from Euclidean space and I literally continue the external momentum space, right? Go to Minkowski space. Then, of course, you can transform to X space. That will give you the analog in ordinary field theory of the time order amplitudes in X space. But you cannot go the other way.
Yes, but in particular for scattering amplitudes, you can just start from all these assumptions. At least in non-local theory, you can compute the concrete amplitude and find its behavior, at least in the weak coupling regime.
But when you say you start from I mean, you're talking about particular theories. Every theory, you have to look at it. You say non-local theory as if, we have a single non-local theory. What do you mean?
Well, you can take, for example, the theory with phi cubed interaction and exponent of box function, for example.
Yes.
In the theory, you can compute the amplitude, actually, in my recent paper with Alexey Koshelov, we did this computation. And we can just look at its behavior in forward limit and all other limits. And then we can use these general theorems, which were derived for general assumptions about amplitudes, to say something about UV behavior or so on. And you don't need to, well, my point is that the conclusion about polynomial boundedness in non-local theories under some assumptions is not related to the possibility of defining Whiteman functions and so on. It's you need just assumptions about analyticity of amplitudes, which can be checked in any particular theory under consideration.
I have some proposal for now that maybe we will move to a little bit next raised hand. Maybe it is related to the current talk as well, so that people get involved. Anupam.
Yeah, so question to Ashok, I think. So in this, just in the worldsheet, at the level of worldsheet, when we do the string amplitude, we know that the answer is always finite. That's famous Grossman-Day calculation, or many other people have done similar computation. And you can immediately see that there are two contributions which can lead to UV finiteness. One is the green function, worldsheet green function, and the other one is also the partition function. Somehow there is this UV IR kind of connection, which always makes it UV finite. But if one looks into the green function part, that green function part works, the worldsheet green function I'm talking about, that's highly non-local. So one would expect that maybe if it translates that into world line picture, and this is what I think many people are doing in this, I think in this audience, that at the level of world line, they're writing down the non-local field theory and trying to see if that can be, whether one can make it UV finite or not. So the question is where things break down actually, or where things help in the string theory case.
So it's maybe I didn't get the question completely. In the worldsheet, of course, yeah, it's non-local, I agree. But that's not related to the non-locality in the space-time. At least I can't see immediately that.
That's true. No, I agree. That's the extrapolation, of course. That's the extrapolation.
Yeah. Because worldsheet is just a tool, right, to compute amplitudes, right? Even in string field theory, you build the vortices out of worldsheet techniques. Out of worldsheet computation. So I don't think the worldsheet non-locality has a direct bearing on the space-time non-locality. Right? And it is true, as you said, this UV-IR connection, the worldsheet UV divergences appear as IR divergence from the space-time viewpoint, right? These divergences as Q goes to 0 that I was describing. Those from the worldsheet perspective are UV divergences, right? But to see that from the string field theory perspective, it's simply that this k square plus m square is going from being positive to negative, right? And that's the connection between worldsheet and space-time. So I would say that the worldsheet is a good description, except that it's not always very convenient, because often you find that you have to define things by analytic continuation. And analytic continuation is, then studying properties of the system, of this analytically continuous system, becomes hard. Right? Because if you are trying to calculate the imaginary part, right, if you don't have an expression to play around it, right? You are saying that it's the analytic continuation of something, and the imaginary part of that is harder to calculate than if you have some definite expression, which is finite. And the same for analyticity. So that's the reason we use string field theory. Right? But it is true that whenever the worldsheet formalism gives the finite answer, it is correct. String field theory is designed to agree with that. Right? And that's the reason why Grossman-Day's calculation we can trust, because string field theory will give exactly the same result. Because when the two calculations agree, it's guaranteed that, or when both calculations can be done and give finite results, it's guaranteed that they should agree.
So Stravan, you are waiting for some time. What is your question?
Well, again, so my question. So I, in all the talks we have in this session, what I see is only scalar field examples from string field theory, string theory with some non-locality. I just want to know how spin 2 interactions or closed string interactions would appear from string field theory, and if there is any strong coupling issues in the string field theory. So
no, we can work at string field theory at weak coupling, because string field theory is, can be built perturbatively, right? So you can certainly adjust the coupling to be weak, and you can apply usual perturbation theory in string field theory. So I don't think that strong coupling is an issue necessarily, right? Of course, you can define string theory at strong coupling, but you can also work with string theory at weak coupling and apply use string field theory techniques there. Right, and there the 3-point coupling, for example, the coupling of 3 closed strings will have exactly the kind of feature that we saw in even scalar field theory, right? This exponential kind of suppression will be there in that case for 3 closed string particles.
the cancellation you talked about in your
So the cancellation
about this.
Yeah. So the cancellation, as I said, sorry, go ahead.
This happens for any spin. I mean, this happens for closed strings. For example, graviton.
Yeah, well, Grossman's calculation was for closed strings, but I think there may be similar calculation also for open strings. I'm not completely sure. Okay, but certainly the Grossman's original calculation was for the closed strings, where they showed that the amplitude in fact falls off at large s in the Minkowski direction. So instead of growing,
And actually some follow.
So that means
some follow-up about this question about translations and string theory. Do you mean that this is related to BRST symmetry and just huge symmetry which describes string field theory? Or what's the reason for cancellations?
This cancellation? Well, see, as I said, from the string field theory perspective, it's very strange, because it's like you are having, each Feynman diagram gives exponentially growing contribution and it cancels. So I don't think it's a consequence of just BRST symmetry, right? The only way we know that the only reason we know that this cancellation must take place is because the worldsheet theory gives this cancellation. Well, from the worldsheet perspective, we don't even think of this as a cancellation. From the worldsheet perspective, the amplitude just falls off, right? Because there you don't sum over Feynman diagrams, right? It's only in string field theory that you see it as a sum of Feynman diagrams. But we know the final answer is given by the worldsheet theory because it's an on-cell amplitude, and that indeed falls off at large s.
I see.
Right? But
okay,
as we discussed earlier, that it has not been, nobody has calculated from string field theory and shown that the sum of the two is small, right? It's just that because you know the final answer is given by the worldsheet theory, you know that the sum must be small.
Related to this point, I don't know why, but it's very difficult for me to understand how the cancellation can happen just thinking about like non-local field theory, so just string field theory. So I don't know anything about string theory, okay, but if you say that all the vertices are like exponentially enhanced for time-like exchange, okay, so not only cubic vertex, but any kind of polynomial vertex, okay. For instance, I cannot imagine why, if I start with a cubic vertex, which has exponential of minus p square phi cube, for instance, then I add a quartic potential with some exponential, how can just this quartic potential cancel the cubic one? I mean, it's very difficult for me to imagine. And,
well, if it's exactly negative of the cubic one, it will cancel, right?
Negative?
Suppose it's just minus of what you get from the cubic, from the S-channel diagram, right? And then it will be 0. Right?
Yeah, you should find but you should find, like, for instance, I don't know, if you have just let's just phi cube and the phi to the 4, okay, with some exponentials, of course. So we take the power also the exponential. So if we just take a 3-level amplitude for, so just with a 2 scattering, okay. So in the case of cubic, we have only the 3-level one. Okay.
Yeah.
Lambda square, let's say. So, and then from the 4 quarting potential, we have one loop diagram. Okay. So what you're saying is that this one loop should cancel the 3-level from the cubic.
No, not one loop. 3-level, everything 3-level.
I know, because if it's just 3-level, it's just basically the contact term for 5 to the 4.
Yes.
But for the contact term, once you evaluate everything on shell, the exponential disappear. Because
no, it can depend on S. Contact term is also non-local.
Well, if I just imagine 5, like exponential of box 5, 4 to the 4.
No, there are exponentials sitting inside the 5-4 vertex also.
Yes. So
right?
For example, exponential of box 5 to the 4, right? You can imagine something like that.
No, not just that. Yeah, okay. Those of course on shell will go away, as you said, right? But there is also a dependence on P1 dot P2, right? If you call the external moment of P1, P2, P3, P4, then the quartic vertex can also have exponential of P1 dot P2.
Okay. Okay.
Otherwise, there will be no cancellation.
I mean, it would be nice to do an explicit computation because no one has done that.
I agree with you.
Just to convince just people that work with the quantum field theory doesn't know anything about string theory, because string field theory is more understandable for people who just know, let's say, field theory stuff. Okay, and thinking about this cancellation is a bit, would be nice to see just the expression of some quartic potential, which will make from simple theory. Yeah. So yeah, please, if you can do it one day, it would be nice.
Okay. Yeah. My feeling is that for the 4-point function, it may not be very difficult because there are this one simple class of string field theories which are used, which uses what is called the SL2C vortex, where you can actually work out everything explicitly. So it's probably possible to work with these SL2C vortices and explicitly demonstrate this cancellation, how it happens.
Okay. Thanks.
Ashok, just a simple query about exactly the point which you mentioned, that you have the divergences, as you said, in string field theory calculation. But I mean, I'm just thinking from the KK perspective, Kaluza-Klein. Once I go above the Kaluza-Klein scale, essentially I have to take into account of all possible corrections into account. I cannot just take one Kaluza-Klein mode and 2 Kaluza-Klein modes. So I have to take all.
Let's do the calculation in 10 dimensions. So there is no confusion. Yeah. So there's a Kaluza-Klein mode, but there are of course massive string modes, and you have to take into account all those exchange modes. Yes.
Exactly.
So the cancellation requires all of those, right? Not just one. Yeah. So you have to add up all the exchanges to see the cancellation.
So in the field theory approach, maybe what Luca is perhaps I mean, pointing out that maybe I need to take into account of higher point corrections in my propagator or something like that to make it finite.
Not higher points. The diagrams are simple. I mean, if you look at the 2 to 2 scattering at tree level, right? There are only 4 diagrams. Right? The S3 and equivalent diagram and the contact term. Right? Only thing is that in the S3 and equivalent diagram, you have infinite number of fields propagating. Okay, but that's just an discrete sum, which can certainly be done. And these, so the claim is that these together should give you this convergence, right? Even the individual diagrams seem to diverge. Now, as I said, because you know the final answer from the worldsheet perspective, we know that this must happen, but it will be good to see by writing down each term separately and how exactly it happens. Okay? That has not been done explicitly.
I see. So if I got it right, you are claiming that a worldsheet symmetry is enough to guarantee cancellation, but from bulk perspective, it's not explicitly obvious. We're still on the way to understand it.
Yeah,
I see. But the worldsheet symmetry, just conformal symmetry, let's say it's SL2R, as you mentioned, it's just enough. I see.
Yeah, from the worldsheet perspective, I mean, basically the way the Gross-Mende did this calculation is they showed that in this limit, the largest large-T limit, is dominated by saddle point. And then they evaluated this by using the saddle point method, the worldsheet integral.
I see. And of course, all of this is applicable to, let's say, 10 dimension, to subcritical dimension, so that we everything rest should be considered as an effective field theory. This in a bit in a bit like comment to Anupam that Kaluza-Klein is okay, but this is more like effective theory from this perspective.
Yeah.
You are starting.
Yeah, in compact, you can compactify, but of course you have to take into account all the Kaluza-Klein modes. As you are going to large still limit, right? You cannot ignore the Kaluza-Klein modes anymore.
But
Yeah,
I
so
think
originally we start in some critical dimension and work out.
Yeah.
But Alexei, I think it doesn't depend on supersymmetry because there was a calculation paper by Jan Lewis and also Dixon and Kaplanowski where they were looking at.
But I didn't say supersymmetry, sorry. But anyway.
Yeah, for non-supersymmetric case, I think, if I recall.
But you
that
need critical strength here. You have to make sure the worldsheet theory is perfectly well defined.
Yeah, that's true.
Yeah, so you need critical dimension, 26 or 10 or whatever you like, but not 4, let's say. Let's put things like this.
Yeah.
I see. And then you can do it. I see. There is raised hand by Gia. Gia, can you unmute yourself?
Hi, yeah. So this is just a follow-up on what Luca said. So there is, so it's not really a non-local case, but there is an example in the Goldstone case. So in Goldstone model, you can do 2 expansions. You can do radial mode and the angle. That's one way. Or you can do phi 1, phi 2, like imaginary part and real part. So you can have generic ON model. And now, so if I choose the vacuum expectation value to be real, so the Goldstone mode is the pure imaginary component. And so if you take this expansion and you plug it in the action, naively you will get interaction phi to the 4th for the Goldstone mode. But we know that's impossible because Goldstone has to be derivatively coupled. And so what happens is that this phi to the 4th is precisely cancelled by phi square times the radial Higgs component. So the exchange by the radial by the heavy component exactly cancels this phi to the 4th. It even sort of a little bit smells like non-locality because, of course, you have a propagator and you can formally represent it as expansion box over M expansion. But for example, that's an explicit toy example when that cancellation happens, and there it happens because of Goldstone theorem. So yeah, so something like this, something like this should be happening also in
I think
words.
the non-local case is much more subtle than this.
Sorry?
It's much more subtle than this Goldstone, this simple example of the Goldstone cancellation.
You mean the
I mean,
string theory?
it comes out only with derivative couplings, of course.
No, you mean the string theory case?
Yeah. It's much more subtle.
No, of course, of course.
No, I mean, it's not such a simple analogy. I don't think so.
No, but I think analogy is pretty good because that's the case when by symmetry quartic. I think this is what Luca was asking. That's the case when by symmetry naively you would think that you have phi to the 4th and phi cube, and by they cancel to exactly.
Yeah, of course, it's a cancellation that you know it's there because of Goldstone bosons have to have derivative couplings. And,
yeah, but they're in string. Still, you also know that it should be there because.
Yeah, but I'm saying that to say explicitly, it's much more involved thing. I think.
You mean to do explicit computation? In string theory, of course, I agree with that. But in field theory, it's straightforward. You see immediately that these 4 diagrams cancel each other.
Yeah, we teach it in elementary field theory.
But by the way, sometimes people get confused about that. They think that Goldstone has phi to the 4th interaction, which is impossible.
Yeah.
Sure. Irina.
Okay. May I ask question? I have very, I don't know, simple questions. What happens if you consider string field theory in light cone gauge? What is your expectation? Because still we have no non-locality, so but some calculation, in some sense more explicit, you can do calculations in open case, string case, as well as in closed string. So what is your feeling about this?
Yeah, I think there is a recent paper by Ted Earler and maybe somebody else where they tried to take the string field theory in light cone gauge and then try to make connection with the light cone string field theory, which of course is a much better behaved theory, right? At least in the X plus minus, it looks local. I don't know how far they have gone. Maybe I should look up the paper again, but maybe you can also have a look. I think that's the only paper I know where they try to start with this covariant version of string field theory, which looks highly non-local, and then try to gauge fix to go to the light cone gauge.
Okay.
But basically, they have a highly non-local field definition, which relates the string field variables from the covariant formulation, the string field variables in the light cone gauge string field theory.
Okay, thank you.
Okay. So, who else? So Terry, you have.
Yeah,
yes,
I
yes,
wanted
sure.
to ask Ashok, in fact, that's a good point, that as far as I know, there is no actual proof that string field theory in a covariant formalism versus light cone string field theory are equivalent. I'm not sure what the status of that is.
Let me try to see if I can find this paper by Ted Earler and his collaborator, then I can at least put it on the chat.
I don't understand how they can't not be equivalent. They give the same S matrix, so they must be related by some kind of field redefinition, mustn't they?
Yeah. But the question is whether to what extent one can prove this directly. Yeah, okay. This is in the context of open strings. It's
Well, I've seen statements in the past, by many people working on this, that it's an open issue that how the two are related. It's not obvious that they're equivalent because, as you say, it's not obvious that you can make field redefinitions that bring one into the other.
Yeah, there is a subtle point there. I suspect that the relation is more than just a field redefinition. I suspect that they're also using perturbative localization. That is, they're taking the covariant field equations and you can localize them in one, you can use perturbation theory to localize them in one degree of freedom. So I suspect that that's going on.
Yeah, I think they also have to do a partial gauge fixing to go from one to the other.
Yeah, that's true. I mean, gauge fixing at the level of the infinite number of fields, right?
Yeah. So it's a combination of field redefinition and gauge fixing, and then perhaps something more. I mean, I just put the archive number on the chat.
Yeah. Well, I believe there is some further question from Irina Arefьева, right? Can you unmute yourself? Irina Yaroslavna, do you want to ask some more question?
No, thank you. Thank you. It is too late. So.
Okay.
Okay. My questions was just I try to remember. Okay. Just go somewhere. I would like to ask you, what is your feeling about high spins theory? Do you expect some non-locality for high spin theory? So, or you believe that there is no at all a finite field truncation, self-consistent field truncation? So, like this is in some sense a general questions, but maybe it's related with this activity. So my question is more general speaking, what is your expectation about high spin theory? Do you expect that such theory should exist? Or I mean a covariant version. And do you expect that this finite spin, high spin theory should be non-local one or what?
This is for
It's indeed a generic question.
Yes, well, of course, this is not maybe for you, but just your general feeling. It would be nice to know.
Yeah, I don't know. I think that it seems hard to imagine that a massless higher spin fields will exist in flat space-time. Right? I think there are general results that you cannot have interacting massless higher spin theory in flat space-time. But in ADS, I think there is a much better chance of CF type theory. Right? And it's generally believed that it's the very strongly carved ADS which will have this massless higher spin theory, right? As some kind of limit of strength theory. But that's, all I can really say in concrete terms. Right?
Okay, thank you.
Maybe others can comment. I think this is quite a general question.
Anyone with a comment on consistent high spin theory?
As far as I know, there is no actually Lagrangian formalism, general Lagrangian formalism for high spin. I mean,
yes,
these investigations are in terms of equations of motion only. Yeah. So it's hard at this point to say whether you can have a field theory in the usual sense that accommodates arbitrarily high spins, unless you are like in string theory, you have an extended object under a geometrical object underlying. But in terms of the standard high spin theory, what goes under that name, Vasiliev was one of the originators of those investigations, right? This is all strictly at the level of field equations, as far as I know.
And they need an infinite number of fields. Is that
yes.
So, sorry. So
Luca, you have some. Yes. I think you proceed, and then Luca already asked.
No, I just wanted to ask you whether you said infinite number of. So it should be like infinite number of those high spin fields, in those theories, or.
Yes, as far as I understand it, I've heard talks on it, and I think that's true. It's not subtle or anything. It's like Terry said, you start with the equations. You can, from the Weinberg's paper on Feynman rules for any spin, you know what the free theory has to look like. You specify its spin and mass, you know identically what the linearized equation is. And then demanding positivity says that there have to be some zeros in field space, just like the zero in Maxwell theory, right? If you take a second d of df mu nu, you get zero. And you then ask the question, okay, well, what can I put on the right-hand side of the equation that would be quadratic or higher and would have that zero in field space? And the answer is there's no finite number of terms that'll do it. You have to keep adding new ones and new ones and new ones.
And they can be massless and degenerate, you mean? The series, or the mass should grow.
Well, I think string theory is an example of a case where the masses grow.
Oh no, their mass is growing, right? There's no problem.
So if you just take a component representation of string field theory, that's a situation where it achieves that, but the masses grow.
Yeah. If masses grow, then at least there is one example. The string theory and its derivatives.
But there are other examples.
I mean, with massless and infinite number of fields, I mean, theory with infinite number of massless fields, that is, I don't see how that can be coupled with Einstein gravity, because immediately we'll get I mean, in Einstein gravity, there is this black hole. Black holes, they put bound on the number of species, because the black hole has to evaporate thermally, and if you have infinite number of species, black hole would just explode. And so there is no way to have infinite number of species with finite Planck mass in Einstein gravity. So I think there is just no go to have degenerate spins, the degenerate massless.
I think this is done in ADS normally. I mean, if you
ADS is fine, right? In ADS is fine.
Infinite number of massless fields in ADS is okay.
Yeah. In ADS, this black hole argument doesn't hold.
I think this will also true for ADS or de-Sitter, because anyway you get a mass, effective mass.
Exactly.
For the gravity.
Yeah.
Also, Robert, you have written in the chat. Do you want to comment?
Robert Brandenberger, there is a question, maybe.
Yeah.
He has.
Robert, are you around?
Yeah, I'm around. I was listening.
Yes.
I don't really have anything to contribute to this high-level discussion. I'm learning.
But you had a question somewhere, so
no, but the question is very interesting.
Yeah.
Well, okay, so I have yeah, that's right. The question related to the cancellation, to the finiteness. Is it the extended nature of the string that is responsible for the finiteness?
Yes, I think so, because the reason that we have these exponential suppressions at the vortices is precisely because of the extended nature of the string.
So in a general effective field theory, one would, in a general non-local point particle effective field theory, one wouldn't have this.
That's true. Yeah.
Robert, when you're talking about finiteness, do you mean finiteness of the loop amplitudes or finiteness at the large S?
I mean finiteness at large S.
Oh, finiteness at large S?
Right. So the idea is that the fact that a string has a finite extent, that will cause everything to decay in the far ultraviolet.
Yeah, see that from the explicit computation, that is the reason why it decays in the Euclidean direction. But why it decays in the Lorentzian direction, I am not completely sure that that's related to finite size of the string, although it was certainly derived from the worldsheet formalism. So indirectly it is related, but I don't know whether one can see from direct physical argument that it should have this fall off for finite for large S in the Minkowski direction. So I would say that it's the UV finiteness is certainly because of the finite size of the string.
Can I say something about this question?
Yes, go ahead, please.
Sure. In a general, as I just said, that covers the string case. But in a non-local field theory case, there is something similar implicitly, that the non-locality means smearing of the interactions over the non-local scale. There is a characteristic non-localization scale, and that implies an extendedness, a smearing, right? Actually, this is related to what I'm going to talk about tomorrow. So in that sense, the fact that you put in a non-local interaction implies some extendedness. In other words, there is a region, right, in Euclidean space where things are well defined, where you have some extension, right, some smearing, some loss of resolution over a certain region characterized by the non-locality scale. So to answer Robert's question, in that sense, you implicitly put in an extension.
You see that this is not sufficient. That's the point which Ashok is making.
No, yeah, no, it's sufficient. If you have a well-defined Euclidean theory, sufficient for the fall of Ashok along the Euclidean directions. Then the question is, when you analytically continue to Minkowski, what happens along the Minkowski real axis asymptotically for large S? That's a different question.
But also one can entertain the question that if I'm really dealing with non-locality, do I really require a Minkowski prescription?
Well, the string field theory examples shows you that in that case you don't, right? But for a general non-local theory, I would say yes, you would need that, unless somebody finds some underlying reason where that you can put in that it assures also good behavior along the real Minkowski axis.
But that's the question. Since we have lost the locality, so what exactly does the Minkowski signature means there?
I don't understand the question.
I'm sorry, I'm not understanding that. We live in Minkowski's signature. How can we not have a Minkowski signature version of the theory?
Yeah, I agree with you what you're saying, but I'm saying that suppose if I'm dealt with some really highly non-local system, does it really make sense to talk about Minkowski spacetime there, or maybe I can do everything should be done in Euclidean spacetime?
But then you continue, and I mean, you define the amplitudes by analytic continuation, right? Even in ordinary field theory, strictly speaking, any rigorous definition of field theory can only be done in Euclidean space. You cannot even do power counting in Minkowski space directly. Mathematically, it doesn't make sense.
Mm-hmm.
So everything is in Euclidean space, and you analytically continue the external momenta, right? The correlation functions.
Exactly, but
in Minkowski space. That's the only way we define physical amplitudes, or physical anything, physical observables.
The UV momenta or the infrared momenta?
Sorry?
The UV momenta or the infrared part?
The external momenta for whatever regions you want to consider them, everything.
So your definition, just to understand the definition, so your definition of non-locality is basically whenever you have some resolution limit in a theory, that's what you would call a non-local theory.
Yeah.
Not really a theory, some kind of action.
No, that's the physical reason underlying the non-locality, and in fact.
So then gravity is non-local.
There are arguments, that this is happening in any case, right? In any experiment, we cannot localize things beyond a certain fundamental limit once you take gravity into account.
Yeah, that's sure. If you take gravity into account because of black holes, right?
Essentially, yes, horizon formation, right? I mean, something happens.
Yeah, black holes.
Even if you don't have a real horizon, I mean, it's a controversy, right? Like in string theory, where
that's irrelevant. That's irrelevant because I discussed yesterday in my talk. You can formulate this softening. It's in the language of S metrics. That's just softening. Yeah, so you will try to you try to scatter hard quanta, and they will soften, and that's the way theory responds. So horizon, no horizon, that's a language. I mean, you can call it horizon. You can call
I completely agree with that statement. Yeah.
Right. Yeah. But
so would you then call
that's your. Sorry.
Would you then say that GR has a non-locality embedded somehow? GR plus.
Yeah, that was my question. So then you would say that in this case, I should say that this is effectively non-local. So we should say that effectively gravity is non-local because of this feature.
Well, to me, non-locality means that the field equations have no finite number of derivatives of the fields in them.
Yeah, that would be a bad non-locality. So that's what, in other words, I mean, so non-locality could be completely crazy because you could say a theory that has an action at a distance is also non-local. But gravity, it looks like gravity gives you this limitation of the localization length. So and then. I don't know. Now it's a question of language. You want to call it that locality or not?
Actually, that's the topic of my talk tomorrow. So, yeah, I mean, gravity really forces you to some kind of non-locality. So the question is how you formulate this in field theory.
Yeah. So I would not use that language of non-locality, strictly speaking.
Well, whatever you want to use.
But of course, as long as we understand what you are talking about, that's fine.
Yeah, I mean, the proper way to formulate it is, how do I sequester various length scales, right? So that I incorporate the fact that there is a limitation to my localization in any type of experiment.
I mean, let's take QCD as an example, right?
Yeah.
So imagine we take QCD. Sorry, did I interrupt you, Luca?
No, please.
So imagine we take QCD. Let's assume that we have pure glue, let's say, or I don't know, heavy quarks or something. And so imagine that you are a low energy observer, or even we can even take master quarks. And imagine we are low energy observers. And now we are doing experiments and we want to probe short distances, arbitrarily short distances. So you would encounter the same problem there. You would see that every time you want to, you produce high center of mass energy, you scatter, you get a bunch of mesons and long strings and things like this. So effectively, an S-matrix observer in QCD will not be able to really, directly probe distances, short distances in that sense. Now, yeah, that's a limitation of resolution within a given theory.
No, but that's not fundamental though, right? Because I can, send in
yeah, that's the interesting
an
question.
electron or a neutrino, right? And see the quarks. That's deep inelastic scattering.
That's why I gave you an example of of certain theory. I gave you an example of a theory in which you have an S-matrix observer, and for an S-matrix observer would have a full information about theory, but would not use the language of short distance physics. Okay, so for an S-matrix observer can fully characterize a theory because that's the way S-matrix observer can define theory, and the asymptotic states are hadrons and glue balls, and asymptotic states are not gluons and quarks. So this observer doesn't even have to use that language. So that's what I meant. So somehow, yeah, you could have an observer which has sufficient information about the theory, but is not necessarily thinking in terms of some short distance.
Yes,
degrees of freedom.
Absolutely, yeah. But the point is that if you consider all interactions that we know of, gravity is very special because it's universal, right? For all the others,
I fully agree.
And I can make things neutral under any other interaction, but not under gravity because it couples to energy. Yeah? So it forces you to this.
No, I fully agree with that. Of course, I fully agree with it. And that's what I tried to discuss in my talk. That was my point, that gravity, the language of multi-graviton amplitudes, exactly tells us this directly in the S-matrix language. Right? Oh, that of course. Yes.
Yeah, maybe if I can just make a comment on the.
Yeah, sure. You have the only raised hand.
I see. Still
looks like a bit late in some time zones.
I forgot it was raised actually. Okay, so no, I think that we should maybe distinguish these two kind of non-localities, because so the non-locality were at least mentioned in the case of string field theory and local field theories, as Woodard said, we have these higher infinite order derivatives in the equation of motion. Okay, instead in the case, so we see non-locality already in the starting Lagrange, in our 3-level Lagrange, we see already non-locality. Okay.
Yeah, I agree. Yeah.
And instead, in the black hole case, you see a non-locality, which is a kind of collective emergent phenomenon.
Exactly. Okay. That's exactly what.
And basically, mathematically, you will see this non-locality in the spectral function, basically, because you will have some enhancement, exponential enhancement.
Thank you. Thank you. Exactly. That's what I was trying to say. That so in those type of theories, I would be a little bit careful to use the language of non-locality, or at least to define it very well. To define it properly, to distinguish from these other type of theories where you have already at the level Lagrangian high derivatives and this kind of stuff.
Yeah, let's say
exactly. Yeah.
In the case of non-local theories, non-locality, people just mean non-polynomial Lagrangians. Let's say non-polynomial in derivative.
Right.
Yeah.
Right.
But
I agree. Yeah.
If I may say, because you see the graviton is massless, so even in Gia's case, in principle, he can write down all infinite tower of higher derivative terms. Nothing stops him from doing that.
Yeah, but no.
But I don't need to.
Yeah, I mean,
You don't need to, but you can in principle write it down. I mean,
yeah, what I'm saying is that even limiting myself with simply Einsteinian gravity, Einsteinian vertices, without high derivatives, there are only two. That's an only two derivative theory. This phenomenon of softening is taking place. So therefore, it's not because theory has high derivatives, but because of the structure of the theory. So because gravity is very special, it couples to all the
Yeah, indeed, so, I think the good maybe just one very quickly. I think the good terminology maybe to use in the case of gravity is that the theory is non-localizable in the sense of JAF, where there is this basically exponentially growing spectral density.
I agree. Yes.
Okay. Yeah.
I agree.
Yeah. Sorry, Terry, I interrupted you.
No. What I was trying to say is more like what Gio was saying, that if you start with a theory that looks local, but if you take into account that the fields cannot be localized because of gravity beyond, or any quantity beyond a certain scale, let's say of the order of Planck length, then even though you think that you are in a local theory in terms of the Lagrangian, if you take this into account properly, then you'll end up with the, if you want to call it effective theory, if you want to, that will be non-local, right? I'm not talking about putting in any explicit cutoffs. You integrate over all moment, all x, but the theory has already implicit non-locality that will show up in the final formalism, which looks like a non-polynomial Lagrangian.
Let's see. So yeah, maybe this is what you mean, and probably I would agree with that. So in other words, we can start like this. We can say, suppose we do some. We are in the process of finding out what the theory is. We do a bunch of experiments, and we recover in deep IR Einstein Lagrangian. And then from this Einstein Lagrangian, we do some scattering experiments, blah blah, scattering computations, and then we understand that there is this effect of non-localizability because of this black hole formation. And now, once we learn that, then we have to face the fact that around the Planck scale, or precisely around the point where black holes and particles meet, there are degrees of freedom. So Einstein's gravity, we thought that it was a theory of a single massless degree of freedom, but in reality it's not, because there are micro black holes. Because since we have big black holes, there are also small ones, and then at Planck scale we can no longer call them black holes. And so, in that sense, Einstein gravity sort of tells us that there necessarily are some degrees of freedom, some resonances around Planck scale or around string scale. But let's talk about pure gravity. And then, then of course, if you integrate out those resonances, you would get some additional terms in your low energy effective Lagrangian. So maybe that's maybe that's the way I would recover what you said. What you said somehow through that, through the knowledge that in other words, there is a separation point where black hole degrees of freedom, collective degrees of freedom, meet particle degrees of freedom, and that's the Planck scale. So in that language, I would agree that with that knowledge, yes, we could say that we already have some sort of high derivative terms present in Einstein gravity, right?
More than the high derivative, maybe the interactions would be non-local.
Yeah. That's what I'm saying.
Well, non-local in that sense, in the sense of having high derivatives, and I don't know. Could be. Yeah, I don't know.
Yeah, some effective action.
That's what I'm going to be talking about tomorrow. So, trying to formulate this kind of thing.
But okay, in the case of black hole, at least there is some, savior, that because there's a horizon. But what happens when we talk about the cosmological context? So there, what would happen? Because there's as such, there's no horizon to, help me.
What do you mean the cosmological? I mean, that's a long distance.
Or I mean, I can go inside the black hole. I mean, and then I can talk about the time dependent metric. So I think I don't know. I mean, how would all these arguments would go through there?
Oh, you mean for the applying to the cosmological spacetime?
Yeah.
For example, the Sitter space.
Yeah, yeah, one could take this.
Like that. Well, I mean, the story with the Sitter. Okay, okay, my talk was about something else, but in S-matrix formulation of quantum gravity, the only way to talk about the Sitter is to think of it as an excited state constructed on top of S-matrix vacuum, because the Sitter itself has no S-matrix. So the Sitter, for example, in string theory or in any S-matrix theory of gravity, the Sitter cannot be a vacuum. That's impossible. Even approximately, it cannot be a vacuum. And sometimes we forget about that. So this is really fundamental. So the Sitter being a vacuum is linked with decoupling gravity, or string theory. This is the same is true in string theory. So therefore, in an S-matrix theory, the Sitter can only be viewed as an excited state on top of Minkowski or on top of any other S-matrix vacuum, for example, ADS or something. So therefore, that's the only way to treat it. I mean, and so then, okay, at the end of the day, then what turns out is that there is some anomaly in the Sitter, and there is some anomalous. There are some anomalous processes which tell you that the Sitter has a finite quantum break time and this kind of things. But that's a separate question.
No, that's a fair comment. Yeah, I agree.
Right.
So
no,
there is some.
I was worried from the singularity perspective, like cosmological singularity. There, the situation becomes much more dire.
Yeah, I agree.
So there is some practical comment on the way. In fact, a lot of this will be topic of tomorrow and day after tomorrow. So in order to everyone to feel not so much restricted, I think it's up to Luca and Sravan. Perhaps we can continue discussing, but I kind of stopped managing all of this. So you should just unmute and try to talk. Especially Luca, if you want to say something with your raised hand, you want to unmute yourself.
Unmute, please.
Sorry, I'm
Luca.
Yeah, I'm here.
If you want to say, unmute yourself.
Yeah, sure. No, I didn't want to interrupt because there was a discussion going on. So
I'm just mentioning that it's a bit late to many people.
That's why. Let's go
back, for example.
Yeah, indeed. Let's. Yeah, it's a bit late. So let me just ask one question, maybe to Olaf. I don't know if Olaf is still around. Just to go back to our speakers today.
Barely.
Hello, hi, Olaf. Maybe it's a naive question, but since this workshop was about ghosts and unitarity, higher derivative, and all these things, okay. I would like you to understand, at some point you mentioned that by doing some reparameterization of your polygon of action, I think, you could like make, remove this high order curvature term and so make the theory, make string theory ghost free, right? That's what you
well, I didn't phrase it in that language, but you can think of it that way.
Yeah,
yes.
yeah. So yeah, I remember in that language. So now, yeah. So basically, that's what I know about the ghost freeness condition. So, but how does this parameterization works? Because to my understanding, basically, you can make many type of reparameterization. Okay, and you can kill many of the curvature terms that you have in the action. You can only keep all the topological invariants. Okay. So how can you, I mean, which is the principle of the Gaudio? Because it seems that there is lots of freedom, okay? So how can you really, for instance, why you can remove this by square term and avoid this Gauss instability?
Well, I mean, so in standard theories, the story is that well, you ask me why it always works to all orders?
Yeah, I mean, yeah, why it works.
So you know that if you have Riemann squared in four-dimensional gravity, that theory has a ghost. So you say you redefine the metric to make it to Gauss-Bonnet, and so you remove the ghost. And you now are you asking why this is always possible, or?
No. Why in string theory there is no ghost problem when you take these alpha prime corrections in higher curvature?
Well, I mean, in our case, we didn't actually care about this. the ghost problem, we just try to see what are the most general field redefinitions you can do. So what's the simplest form of the action at the end of the day? At the end of the day, and it turns out you can always bring it to a form that only involves first-order time derivatives, and that, of course, is directly linked to this general discussion. But for us, it was just a technical simplification.
Yes, I was more referring to the paper by Zwieback, where he shows with this field redefinition that he can do he can remove basically these curvatures that are basically unstable. Okay.
Yeah,
so,
yeah.
But it seems that you have lots of freedom when you can kill all these high order curvature, right? I mean,
yes.
With this, and is there any? I mean, I don't know, because in principle you can also kill R squared term, right? If you want. You don't, I mean, you can kill any kind of term you want. The only one that are safe from this field revalorization are like, from this coordinate revalorization are just the topological invariants, from what I remember. So,
well, I mean, so if you think of, for instance, let's take 10-dimensional string theory, there you have a Riemann squared term, first order and alpha prime, and that one you cannot remove. You can remove Ricci squared and Ricci scalar squared by redefinitions of the metric, where you cannot remove the Riemann square term. So that's one contribution that is invariant, and it's there. So it's not, I mean, it's not true that anything goes, but in the reduction to one dimension, there you have this feature that you can only that you have only first order time derivatives. So what you can do, of course, is in the Gauss-Bonnet combination in any dimension is a total derivative at the quadratic level if you expand around flat space, right? So you can always set it up in such a way that the free theory has only two derivatives. So that's what Ashram referring to. And so that perturbatively it's still okay.
But I think, Olaf, one should have done the calculation in an expanding background, not in a Minkowski space, and then use cosmology. Strictly speaking.
Yeah, but I was not doing anything. I was not doing any such thing. That was just here for the sake of argument.
Okay.
So look, we repeat what we did. So we write a summary and
wait,
write,
so I don't know what time is it actually.
So
so
we should continue tomorrow. I mean, for us today. So
okay. So also today I think was very nice day. We had lots of interesting talks and especially intense discussions. Okay. And actually we also finished at the same time like yesterday. So here in Japan is 15 to 5 a.m. And I think we can maybe meet. Let me just thank again Richard, because also Richard is in Taiwan. Also for him it's quite late.
And Ashok, what time is it in India? It's also quite late.
1:15 here.
Whoa, okay. Then thanks also to Ashok. Actually, let's thank again all the speakers.
Thanks to everyone, especially to speakers of today.
All the speakers of the day. So we can meet again tomorrow. We will have the first session will be on. We will see several approaches actually in the first session on Lorentz invariant, like Horava-Lifshitz approach. We will see some non-local approach, and we will hear a lot on higher derivative gauge theories and so on. Okay. While the second part will be mainly focused on the non-local field theories, and we'll have Alexi, and as also Terry said, he's going to speak tomorrow. And I hope the discussion session will be again very stimulating like it was in these first 2 days. Okay. So thank you very much, and see you tomorrow. Okay. Have a nice day.
See you tomorrow.
Bye bye.
Bye.